Time to do an example with drying of surface wet goods. Heat-sensitive drying goods is to be dried concurrently, making sure that the temperature of the air does not exceed 52 degrees centigrade. The fresh air is 20 degrees centigrade, warm with a relative humidity of 60%, and is preheated with a dry hot surface before getting in contact with the drying goods. The incoming drying goods, 200 kg of dry material per hour, has been preheated to the wet temperature of the incoming air. Incoming drying goods has a water content of 0.8 kg of water per kilogram of dry matter and should be dried to 0.2 kg of water per kilogram of dry matter. The outgoing air can be assumed to have a relative humidity of 100%. Calculate the required energy and airflow. I would recommend you to pause the video here and try for yourself. With the things you have learned previously on moist air, together with what was said in the video on how to supply energy, and this Mollier diagram here, you have all you actually need. Okay, I hope you succeeded. Let's now go through the solution. First, we find the fresh air in the Mollier diagram. 20 degrees centigrade is this line here, and 60% relative humidity is this curve. So this is point 1 in our diagram. The drying goods must not become warmer than 52 degrees, which means that we can safely warm our air to 52 degrees. When we warm up an airflow, the water content X remains constant. Thus we draw a vertical line up to 52 degrees. We see that the wet temperature of the heated air is 25 degrees, which means that the drying goods are to be heated to 25 degrees. Since the line for adiabatic cooling is the same as the wet temperature line, at least for modest temperatures and water contents, the air in the adiabatic dryer follows the T wet equals 25 degrees line. And the outgoing air is said to have a relative humidity of 100%. In a later video, linked above there, we will see why that is actually not reasonable. But for now, let us just pretend that it's possible to reach 100% relative humidity. We can now read the water content X1 and X2 as 0.086 kg of water per kilogram of dry air and X3 as 0.020. We can read the enthalpies H1 and H2 as 42 and 75 kJ per kilogram dry air respectively. The careful reader will also note that the enthalpy H3 is slightly larger, 76 kJ per kilogram of dry air, than H2. This since the airflow G3 contains more water vapor than the flow G2, and the fact that we use the energy unit kJ per kilogram of dry air. Since all air that comes in also goes out, the airflow measured in kilogram of dry air per hour remains constant, and thus G1 equals G2 equals G3 equals G. With W denoting our drying goods in kilogram of dry goods per hour, our water mass balance for the entire system becomes W times X in plus G times X2 equals W times X out plus G times X3. Our only unknown in this equation is the airflow G, and we get G equals W times X in minus X out divided with X3 minus X2. So 200 times 0.8 minus 0.2 divided with 0.02 minus 0.0086, which gives us G as 10,526 kg dry air per hour. Our energy balance becomes G times H1 plus Q equals G times H2, which gives us Q equals G times H2 minus H1, so 10,526 divided with 3,600 times 75 minus 42, or 96.5 kilowatts. To check our calculation, let us recalculate our energy requirement to the unit kilojoule per kilogram of water. The amount of evaporated water is W times X in minus X out, So 200 times 0.8 minus 0.2, which is 120 kilogram per hour, or 120 divided by 3600, 0.0333 kilogram per second. If we divide 96.5 kilojoule per second with 0.0333 kilogram of water per second, we get 2895 kilojoule per kilogram. We may compare that with the evaporation enthalpy of water at 25 degrees, which is 2442 kilojoule per kilogram. Our energy requirement per kilogram of evaporated water is thus a bit higher than the evaporation enthalpy. This is a reasonable result for drying with air. In a later video, we will investigate why the energy requirement is higher than the evaporation enthalpy.